All right, so today I think we're going to catch back up and be back on schedule. All right, so just to review a little bit about how we got to where we are right now. Okay, first day of class we learned sort of the fundamental concept around like how computers do what they do, which is they count and they do math on binary number systems. Okay, we learned how to count in binary. We learned how to count in hexadecimal, which is a way that is a good abstraction for binary that is a little bit easier for us to look at. And we talked about sort of how a computer can leverage its ability to do math to represent audio or sound. It can take the difference between sound and audio is sound is happening in the air, and audio is the electrical representation of a sound that happens in the air. Audio is when it's electrically on a wire. Digital audio is what happens when a computer tries to represent that electrical audio signal using binary numbers. That's digital audio. So it's taking that electrical signal and expressing it using binary numbers. And it does that by taking what are called samples of that electrical signal at some predetermined interval. And that interval is called the sampling rate, and it needs to be at least twice as fast as the highest frequency of audio that you're wanting to represent. So generally speaking, the lowest frequency that we tend to work with from a sampling rate point of view is 44,100 hertz, or 44.1 kilohertz. We usually don't sample at a lower rate than that, except in some very, very rare exceptions. And these days, often we're sampling higher than that for a lot of reasons, not all of which are meaningful, some of which just make us feel better, but there is room for those higher sampling rates, but you got to get a lot of other variables right in order to really see the potential advantages of that. But as long as you're sampling at least that 44,100 hertz, you should be able to get adequate resolution to represent just about anything. And then it does that sample that it captures represents essentially an amplitude value of the analog audio wave, and that sample can be of varying sizes. And what I mean by that is the number of bits it's using to count that number. It could count that number using 8 bits, or 16 bits, or 24 bits, or 32 bits, or 64 bits. It just depends. But the more bits, the more detail it can encode from that amplitude point of view. The difference between loud and quiet. How much resolution does it have to capture whatever that electrical level was? Okay, so more bits, more resolution. But more bits means bigger sample, which means bigger file that you have to keep track of and store on your computer. And more bits also is more work for the computer to deal with. So you kind of got to think about that. And then last week, we looked at a little bit of the computer engineering side of things about how does a computer actually work? What does it really do? What are the important things inside of it that you have to be aware of as you use it? Things we learned about: inputs, outputs, processing, and storage. Those are the 4 functions of a computer. Computers collect input from the outside world, either from human beings or other computers, and they send information out to the outside world, either to human beings or other computers. And then they can also process the information that they have collected before sending it out, and they can store the information they have collected without sending it out, or both. And we learned a little bit about the different kinds of software there are. That there's something called firmware, which is kind of the lowest level piece of it that kind of tells the computer how to interface with all the little different bits of hardware that are on that board. And then you get the system level software, called the operating system, which basically provides a user interface for you, the human who is working with the computer, and translates information that it gives to you and you give to it into commands that the firmware can understand, that the firmware can then relay to the hardware. And then the third one is application software. And this is a piece of software that is designed for a specific purpose, for whatever it is you're trying to do, which could be a lot of different things. But in the context of this class, it's doing digital sound, digital audio. And we're going to look at a few different pieces of software over the course of the semester that you can do that with. So today I want to kind of put all those concepts together and look at how do all those ideas come together to let a computer do sound or function as a tool for you to make sound. So this is a animated system diagram for a digital audio workstation. And we're going to go through each part of this, one little piece at a time, make sure you understand what every part of this means. And because next week, you're going to have to do this. You are going to make your computer do this for an assignment starting next week. Okay? So the assignment that you're going to have is to do a recording. So I have made some connections with some acting students who have volunteered to come and let you record them. They're going to bring like some commercials, to voiceover commercials, and they're going to have a few of them. And I'm going to pair you up with at least one of them. The grad students, I'm going to have you do two. And you need to reach out to them and make an appointment to meet them over here in the booth and record them. And to do it this way on your computer, get a microphone, going into the interface, the whole thing we're going to talk about today, record it, and then turn it into something. So I want, you're going to edit it down and make it sound good, and you're going to put a little bit of like commercial-y music to it and give them a little 60-second demo reel that you can give back to them that they can use for, that's what they're in for it. Yes, they know that the main part is to come and help you learn something, but the carrot I dangled at them is like, if the student that you're working with happens to do a good job on their homework, then you'll get a free demo reel out of it that you can float around for auditions and stuff. So, so I hope you'll do a good job for them, although they know that you might not, and it's a gamble. But anyway, so let's talk about it. So the first thing is the microphone. Now, you're familiar with microphones, hopefully already. You've touched them and used them and done things with them. And you know that, hopefully you know generally how a microphone works. But what it's doing is, a microphone is called a transducer because it converts one form of energy into another form of energy. And in this case, it's converting acoustical energy into electrical energy. So it's taking that acoustic sound wave of air pressure amplitude changes and encoding it into an electrical audio signal. And that's represented by the red line, that's jumping around as it comes out of the mic. Okay. So this is analog. It's not. There's no binary involved here. There's no math involved here. It's an electrical thing that's going on, and it sort of does what it does. I mean, a microphone. There's not a whole lot you do to control what the microphone does. In fact, a lot of them are completely passive, meaning they are working all the time. They're doing the same thing sitting in a drawer as they're doing sitting on a mic stand. They're just completely passive devices that are just constantly trying to do that thing, converting acoustical energy into electrical energy. Some microphones are active in the sense that they only really work if you provide them a little bit of an electrical signal to energize them, and then they can do it. Those would be like condenser microphones. But if it's a dynamic mic, it just does the thing, and there's not much you really need to do with or about that. But a condenser mic, if you have to send it some electricity, it sometimes will have some parameters on it you can manipulate, like it might have a built-in filter to filter out low frequencies or something. Or it might have like a sensitivity adjustment on it to so you can kind of figure out what is the nominal voltage level that's going to come off the back of it, and you can kind of have a couple of options for that. That's important only in this context, really, of what you're plugging the mic into. Sometimes the thing you're plugging it into might need more or less nominal voltage. The other thing sometimes those active mics, those condenser mics have is the ability to manipulate the polar pattern on it. So you can switch it between like a cardioid or a supercardioid or a figure 8 or omnidirectional, stuff like that. But but by and large, the mic does what it does, and you need to point it at the thing that's making the sound that you're trying to encode. That's the gist of it. Just point it at the thing, and try to get it close enough to the thing that it picks up that and not anything else. And some of its ability to pick up the thing you want and nothing else is really dependent on the environment that you're doing this in. If you're doing this in a noisy environment, it's going to be really hard to get the thing you want without getting everything else. You're going to have to get that mic really close. But if you're in a pretty controlled environment, like a room that only has this one thing happening in it, and nobody else is in there, and nothing else is in there, and there's not a lot of loud, hissy things, and dogs barking and stuff like that, like you get a lot better results. And it's really, really worth the effort to try to find a good place to do this in. It will save you far more time if you spend this time at this point finding a good place to do it. That's the amount of time you spend doing that is far less than the amount of time you will spend trying to clean up that recording that had all that other garbage in it. It's just, what you see on a TV show where they, on like the crime scene investigator TV show, where they have this really terrible recording and they just go find some person in a basement, with a bunch of computer screens, and that person like clicks a little button and suddenly the recording becomes like pristine and clear and you can only hear the person's voice and all that other garbage went away. It's really not. That's not really how it works. It's quite a lot more difficult than that. And although you can clean things up, it always comes with a consequence, and there are artifacts involved in that. So, but generally speaking, point the microphone at the thing you want and try to get it to not pick up anything else by making sure it's in a quiet place away from other things. So then this electrical signal, the next thing that it encounters is, in this scenario, is called your audio interface. Now, the audio interface, or sometimes this is called a sound card, this is a piece of technology that is designed to be between the audio equipment and the computer. And its job, if the microphone's job is to convert acoustic energy into electrical energy, the audio interface's job is to convert electrical energy into digital signals. So it's a different kind of transducer. So you're going from acoustic sound to analog electrical audio, and then the audio interface converts that electrical audio into digital audio. Zeros and ones, it does the binary thing. It's doing the sampling and encoding those numbers and sending those numbers onto the computer as digital data. Okay? So you can see the red electrical signal is going in, and then somewhere along the way it gets converted to this blue stream of zeros and ones and gets sent into the computer. That's what the audio interface does. Now, you really do kind of get what you pay for with these. Most laptops, for sure, these days have an audio interface built into them. And that's been a thing for a long time. And the ones today are quite a lot better than they were even 10 years ago. They're able to operate at pretty high sampling rates. They're reasonably quiet from the point of view of how much garbage inside the computer they're picking up, because everything makes noise, and one of the dangers of putting that interface inside of a tight laptop or something is it ends up being packed in around a lot of noisy things and other circuits that could inject things you don't want into that signal before it gets encoded into digital. But generally speaking, the audio interfaces that are built in tend to work much better as digital to analog converters, meaning like output. They're much better as output devices than they are as input devices. The input device side of these built-in audio interfaces are usually not very good. They're really just designed to pick up a dinky little mic off of like your iPod headset or something like that. If you're trying to feed a really nice mic, like a professional microphone, into the computer, you're going to need something more than what's built in. Okay, and I would argue that even playing back, you will find, especially if you spend a lot of time on ear training, you will start hearing the difference between that built-in headphone output on the computer and something that you would get off of a nice external interface like this one. Okay, because what it does is it gets all of those sensitive analog circuits away from the inside of the computer that has all that other nonsense going on that can mess things up, and it separates it and makes it a lot cleaner. But also, you're not as concerned about miniaturization as you are with the built-in one, and so to make things smaller, you always have to compromise a certain amount of quality to make things smaller. And when you're using an external interface, you can avoid some of those compromises because this is the footprint you're looking for, and so the circuits can be bigger, and therefore you don't have to make a lot of those quality compromises. So these tend to be just better all around. They sound better, they work better, everything is better about this. The main compromise here is convenience. So this is not as convenient as the built-in one. And if the human race has proven anything over the last however many years we've existed, it's that we are so happy to compromise quality for convenience. And that's fine for a lot of things, but sometimes, especially if you're going to do this for a living, you need to be very careful about those compromises. If you're compromising quality for convenience in the work that you're doing, then that means the work you're doing is of less quality. And if you're making that compromise and someone else isn't, then even if you're doing your best job with all the compromises you've made, that person that hasn't made those compromises could do their best job and maybe turn out better work than you, right? So be very careful about those compromises. This is worth avoiding that convenience. Okay. So what's inside of this audio interface? Well, it kind of depends. The main thing that you're going to notice is the number of inputs and outputs it has. So like this one that I'm carrying around here has, looks like two inputs. One of them is, there's a third one here, but I think it's shared. It's a shared circuit. So 2 inputs on XLR connectors or 1/4 inch. And the third one is like a instrument level input, so you can plug a guitar straight in. And I think that routes through like number 2 or something. And then it has 2 outputs that are on balanced 1/4 inch. So this is balanced audio coming in and out. And balanced audio is what's way better at sending signals a long distance without getting noise in them. But it also has a really high quality headphone output that's on a 1/4 inch connector. It's going to be a lot lower noise and much higher quality. This thing is also able to sample, I believe, up to 192 kilohertz, 24-bit, which is pretty good. That high of a sampling rate implies that there's a frequency response capture for this that is much higher than 20 kilohertz. So it's going to be able to encode audio frequencies much higher than 20 kilohertz. And maybe you're thinking, well, gee, Jason, why do we have to care about encoding things higher than 20,000 hertz? We can't hear anything higher than 20,000 hertz. Well, that's true. I don't think you're not hearing those things, but there's a lot of schools of thought about this, and one of them is, and this is the one that I tend to find myself sympathetic to, which is that, okay, yeah, just because I can't hear that doesn't mean it's not interacting with the frequencies I can hear and shaping them. You know, that's what happens when different frequencies interact. They shape each other. That's what comb filtering is, right? And so these frequencies we can't hear are still happening, and they are still interacting with the frequencies we can hear. And so maybe there's some value in capturing that interaction. But I think the even more compelling, there's two other even more compelling reasons to think about these higher sampling rates. One is that the converters in here, we'll talk about in a second, have to do a certain amount of frequency filtering before it sends that analog audio into the converter to be encoded to binary. And it wants to filter out all the frequencies that can't be captured by that sampling rate. So if it's 44,100 hertz, it's going to try to not let any audio frequency higher than 22,050 hertz to go through the encoder, because any frequency higher than that is going to alias as something lower. So it's going to try to filter that out. But as you know, hopefully you've discovered in your experience so far, a filter is also known as an EQ, and EQs aren't perfect. They're not brick walls. Like, you can't just say nothing beyond this will pass. There's a ramp. There's a tail to those things. And the quality of that filter is a big part of what makes the converter considered to be a good converter or a good interface. And so the ability to sample at higher sampling rates really just is more like accounting for the imperfections in that filter, because some of those higher frequencies are still getting through, even though they're trying to get filtered. They're just quieter. But then there's the one other argument for higher sampling rates is one of the things that we do the most as sound designers, one of the sort of most powerful tools in our arsenal when we're designing sound effects and things like that, is to manipulate the pitch of something. And one of the simplest ways to manipulate the pitch of something, if it's a digital audio signal, is to mess around with its sampling rate. Okay, so you take something that is set as a certain sampling rate and you start feeding it through the system slower than that. And you feed those samples slower than the sampling rate they were designed, and that gets interpreted as lower pitch. And feeding them through faster results in a higher pitch. So you start manipulating that sampling rate to get pitch adjustments for your sound design, and if you have more samples than you need, then you can mess around with that with less compromises in quality. You know, there's less artifacts as a result of that. So there's an argument for those higher sampling rates just to get you better results when you start manipulating pitch. Eric, you had a question?
Yeah, I'm just wondering, I have sort of had some accidental experiences with this. Is there a significant difference in the pitch between 48 kilohertz and 44.1 kilohertz?
There can be, yeah. You would notice the difference.
When I was listening to doing one of Wake's projects, it accidentally switched to 44.1 when I was doing 48, and there's significant difference.
Yeah.
Instead of talking like this, you're talking like
Yeah,
this.
changes the pitch noticeably, definitely. So so that's pretty good. The other compelling reason for higher sampling rates is avoiding latency. So we'll talk more about that in a minute. But so let's take a look at what's inside this interface. Well, for the microphone, the first thing it's going to encounter is the preamplifier. And this is an analog circuit. There's no digital happening yet here. This is the same thing that's on a mixing console. It's an analog thing. And what it's doing is, remember that one time when I said the dynamic microphones that are passive, they're always on, they're always doing the thing, they're always converting sound into audio? Well, depending on how loud the thing is they're encoding and how close the mic is and everything, that is going to result in a slightly different voltage. But you really want as high a voltage as you can get before you feed it into the next stage. Because the higher the voltage, the more potential for utilizing that resolution of that bit depth that you're going to use for this. So the higher voltage you're feeding in, now that's a bigger range that the digital number can be used to encode. And so you want that pretty hot. But you really don't want to clip it, as we learned the first week, right? Clipping, you can't recover from that. So you don't want to clip it, but you want it as hot as you can get it without clipping it. And some people will, if they're really not sure how hot they need to get it, but they really don't want to clip it, they'll, on purpose, back off that preamp a little bit and rely on 24-bit encoding to make up for the potential resolution loss. Because 16 bits should be more than enough, but if you can't get the gain structure just right, sometimes that 24-bit signal can save your butt because you just have more resolution to work with. Ideally, you want these to be pretty good preamplifiers. You want them to be really quiet. You don't want them to introduce a lot of their own noise into the equation, because the sampling process already creates noise, quantization noise all by itself. You don't want any other noise coming in. So hopefully this is pretty quiet. It's worth paying for good preamps that are quiet. And this will usually be a knob on the interface, or sometimes you'll be able to control it digitally with a piece of software on the computer. Yeah?
When you say a pretty quiet one, like if you're looking for a preamp, like what's the range of a pretty quiet one, I guess?
It usually will be spec'd in like dBu or something. They might tell you that it has this level of self noise. Usually, if they don't tell you, assume it's probably not that good.
Is there a number that you look at it and go, no, that's too noisy?
Well, it just depends. It's really about how loud is the thing, how high is the signal you're going to be passing through it compared to the level of that noise. If you got your gain structure really good and you're feeding your stuff in really hot, you can have a noisy preamp and you might not notice it because there's such a big difference between its noise and your signal. But if you aren't sure if you're going to be recording really quiet things and you're not necessarily going to get the gain just right, you don't necessarily want, your signal might be really close to that noise. So it just depends. But generally speaking, you get what you pay for there. Okay. So that's what the preamp does, is it just amplifies that voltage, hopefully without amplifying its own self-noise, and feeds that now higher voltage signal. As you can see in the animation here, it came in as a lower amplitude audio signal and it's coming out at a higher amplitude. That's what the preamp's going to do. And then it feeds that analog signal into this thing called the ADC. And the ADC that stands for Analog to Digital Converter. This is a little miniature computer chip it's an input device for a computer chip. And what it does is it looks at the voltage level, and based on whatever your sampling rate is, we've got a picture of one here, of one of these chips, that it can sample up to 192 kilohertz. Pretty good converter. And it's going to look at that voltage 192,000 times a second, if that's how fast you want to have it do it. And it will take a look at that voltage and assign a digital number to that. A 24-bit number, 24-bit number, 24-bit number. And it just keeps doing that. This is another thing. This converter, this is another thing that you get what you pay for. Some of the things that you want to look for on these, if you really get into the weeds on it, is how good are the filters on it? Because it has to do some filtering before it encodes it. How good is that filter? How well matched is it to the sampling rate of the system? Is it gonna, how likely are you to get aliasing? These days, they've pretty much solved that. That's not a problem you have to care a whole lot about, but we used to have to care about that a lot more now. Sometimes these converters have a hard time keeping up. Like they can't do the sampling rates you want them to do, or they do them too slowly, or whatever, you know. But generally speaking, we've pretty well solved this by now. Even the lowest end converters are usually pretty acceptable these days. So this isn't something you have to really worry a whole lot about. The main thing you're going to be looking for is the sampling rate it can do. You know, what's the highest sampling rate it can convert into, and at what bit depth. Just make sure that's enough for what you want. Higher the sampling rate and bit depth, the more expensive it's probably going to be. But especially at those higher sampling rates, you really need to make sure that you've got other parts of the other components of the system that can process higher frequencies, right? Otherwise, there's no point. Yeah.
So, like, I'm trying to find a reason why you would want to use 192 kilohertz, say, to record a song. What is the reason for why you use 192 and not 448?
Yeah. Well, there are a few reasons, some of which are valid and some of which just make you feel better. But to some extent, there's a little bit of it makes me feel better kind of thing, but it doesn't really change anything. But the most common result of this is, you know, there's a big push right now for wider frequency response microphones. You know, microphones that are going to be able to capture much higher frequencies. And loudspeakers that can do that. And the only way you can work with that digitally is if you're operating at a higher frequency for a sampling rate. Now, you go back to that argument of like, well, yeah, but can we hear those higher frequencies? I don't know, but if you're getting a microphone specifically because says it can pick up as high as 50 kilohertz, for example, as an audio frequency, then you're going to at least need 100,000 kilohertz sampling rate to encode that. So it kind of depends on what the rest of your hardware looks like. But the other reasons are that it gives you the ability to do some more manipulation after the fact. So after it's been encoded, the more samples you've got, the more kind of processing you can do on it, like manipulate the pitch and stuff like that without creating new artifacts and new problems. Even though you're going to end up throwing out a lot of that data in the end, having more data to work with at the start tends to be a good thing. But also, there's a latency component to this. Generally speaking, although we're seeing this get faster, generally speaking, these analog to digital converters add about a little bit less than a millisecond of latency into your system. So it just takes them about a millisecond to do the thing that they do. Okay? So the analog audio that goes into it comes out of it in digital form a millisecond later. Although we're seeing it get faster now. You know, I'm seeing it get down to, I've seen some that are as slow as 0.4 milliseconds, which is pretty cool. One of the factors for that latency is the sampling rate. And this is a little bit counterintuitive, but a higher sampling rate tends to have lower latency.
Oh.
Just because it's pushing the numbers so much faster.
Yep.
Because even if it's latent by the same percent, that
Yeah.
percent is less than.
Yes.
That's weird.
Yep.
I don't like that.
Yep. But you know, when the first sort of like 96 kilohertz mixing consoles started coming out, a lot of theater people and broadcast people too were pretty excited about that, especially the broadcast people, because they were like, cool, it's faster. Less latency. You know, I'll have less sync problems, you know. And that was the thing they were most excited about. It wasn't because they could encode higher frequencies. It was just the chip's faster. Okay? All right. So it comes out of the ADC as now zeros and ones. A big long stream, never-ending stream of zeros and ones. And that feeds it into what's called a little controller chip. This is a hardware controller. or digital signal processor. This does a few different things. Like in some cases, this is doing simple things like just lighting up LEDs on the interface and stuff to tell you that things are working. It could also be providing the phantom power to the condenser mic, different things like that. But a lot of interfaces these days have like built-in digital mixers. So like this one has that, where inside of the interface you can actually do a little bit of mixing and routing. Like you can pass inputs directly to outputs and stuff like that. And that's handled by a little controller inside the interface. It doesn't use the computer to do that. I mean, you have a piece of software on the computer that talks to it, but the actual work is happening inside the interface before the audio ever gets to your computer. And that can be really helpful for a lot of things. For example, when you're recording people, they sometimes like to hear themselves back in these headphones. Well, if the sound has to go through the converter, through the controller, into the computer, do all the computer-y stuff, and then come back out, get converted back, and then they hear it. Remember what we were talking about with latency? Sometimes there's an audible delay between when they talk and when they hear it in their headphones because of all the work that has to do as it makes that round trip through the computer. Well, if you've got a little DSP inside the interface, sometimes you can route the audio back into the headphones before it ever has to go through the computer. Some interfaces let you do that before it even gets converted to digital. They can make a little mix link at the analog level and shoot it right back out, and that's instant.
Oh, is that what you can hit like a button there?
Yeah, that's called direct monitoring.
Oh, that's it. Okay, yeah.
Okay, and that's what it's doing is it's basically just like patching the back of the preamp into the output of the for the headphones before it ever goes through all this digital nonsense. And that's instant. There's no latency involved there. And sometimes it'll be a digital loop back, so it'll go through the converter, but the controller will loop it back out, and that's a little bit faster than having to go through all the computer system first and come back out. And what in the world? Oh, there we go. My mouse is jumping over to my iPad. So anyway, there'll be some software on this thing that does stuff like that. Sometimes you can even have like EQ and compression inside the interface before it gets sent to the computer. That can be a little tricky because once you do that, it's hard to undo that. That would be considered destructive processing, but maybe. Okay, so it comes out of the controller, and it's hopefully it might just be exactly the same once it comes out of the controller. Or it might have been tweaked by the controller. Yes.
So, quick question. It's not the most helpful bit, but I'm curious about like, because I know like some people they sell like a blue microphone that's like USB.
Yeah.
Does it have that like converter inside
Yep.
of it?
Yep. So this audio interface box that's represented here, they cram that box into the mic itself, and yeah, that's what's happening. Is all of this, all of these chips are just miniaturized and stuck inside the housing of the microphone, and then you just plug the microphone straight in. But other than that, it's the same. It's got all the same components. They're just inside the mic.
Yeah, because I was like, how does it go straight to digital?
It doesn't. It does all this same stuff. They just miniaturized it and stuck it inside the mic.
And those, though, I assume that they cut out the digital to analog, or do they have like headphone jacks on them?
Some of them have headphone jacks on them, yeah. Yeah, some of them do.
And so then you can cut that out and
Yeah,
have more space.
yeah. Some will. Some will not give you that output, and so all they're doing is the analog to digital, and they don't have to worry about the digital analog.
Do they even need a controller then?
Well, you need a controller in the sense that it talks to the computer, and there'll probably be an LED or two on there to tell you that things are going on, and so it's just small. Yeah, Lee.
I realized when I used the blue mic in Simulating Bar when I was younger, like when I was 18,
Yeah.
I ran into the problem with latency. It had some huge latency problems.
Yeah.
And also the mic was also a podcast mic, so then it had
Yeah.
its own audio jack.
Mm-hmm.
But that audio jack was also overriding the outputs on the computer.
Yeah.
So then it was just like its own computer.
Right.
But it was kind of a problem.
Yeah, so that's some of what can happen inside this controller or DSP chip is it can handle some routing all by itself, and all it's really doing from the computer is getting power, but ultimately it's really operating as a standalone device. And so that's about the settings inside the controller software to decide, am I relaying the audio to the computer or am I just spitting it right back out? That just depends on how it's set up and what you do with it. All right. So it comes out, it's still a stream of digital data, maybe the same or maybe modified somewhere inside that digital signal processor. But then it goes through a cable that, when we made this animation, it was USB or FireWire was the most common, although FireWire is not seeing that much anymore. And USB has evolved a lot. So it's now, this will usually be USB or Thunderbolt these days, okay? And if we have time, I'll talk about the difference. But somehow you connect the interface to the computer through one of those things, and that data then goes through that to this thing. It basically goes directly into RAM, okay? And we talked about RAM last week. You remember? RAM stands for Random Access Memory, and this is this really, really fast storage medium that the computer has to work with, where it stores the digital data as electrical current, and it can access it in any order that it wants at any time. So it's really, really fast, random access. This is where the CPU puts things that it's actively working with right now, okay? So this digital audio comes off of the interface and goes straight into RAM. And the computer's going to allocate a chunk of the RAM to do this task, and this is called the input buffer. And the audio input buffer is a certain chunk of the available RAM that it's going to say, this is where we're going to hang on to this digital audio as it's coming in. Because ultimately, it has to go through the RAM and get to the CPU, and the CPU has to decide what to do with it. And there's a lot of different options of what it might be doing, but those things take time. And the computer has a lot of other things it's doing too. It's not just thinking about your sound, it's thinking about, what time it is, and it's thinking about, whether you just got a new email or not, or it's checking to see if there's any software updates that have come out recently. It's, keeping track of all the other hardware on the computer. It's, running all those other programs that you just leave running on your computer and never shut them down, even though you're not using them. It's doing work on those things. Just because you're not looking at it doesn't mean the computer's not. So the CPU has all that other stuff it's doing. And so it can't direct all of its attention to this audio that's coming in, this digital audio that's coming in. And so sometimes it has to go and work on other things for a nanosecond or something. But the problem is, we're talking about a continuous stream of data. And if you drop any of it, you will hear it, right? You will miss that sample if it disappears. It'll be a pop, when it re-encodes. So you don't want to lose any of that data. It's got to be a continuous, uninterrupted stream, but the CPU can't focus completely on it because it's got a lot of other things it's thinking about. Now, you can help the CPU out a little bit by shutting down stuff that doesn't need to be running. When you're doing this process, when you're recording something, you really should not have your web browser running and, email going and chats going, and all that stuff should be shut down. Just whatever else, all those things you leave on, you should close them all, right? You can make the CPUs a lot happier if you give them less things to pay attention to at one time. You could even disconnect them from the internet.
Yeah, I was about to say, just turn on airplane mode
It can, yeah, because if it knows that it's not connected to the internet, then it's going to shut down all the processes that it usually has to check on things online, right? It's oh, I'm not even connected, so I'll just shut down all those processes, and that's less work it has to do as well. So anything you can do to free up, make the CPU's life a little easier, that means it can pay more attention to your audio. Okay? Yes, Eric.
Well, also if you put it on airplane mode, it also pay attention to what's already been processed. So I mean, say if you were listening to music through the internet, if you already played it, you could still listen to it on airplane mode because it's already processed.
Well, it's been downloaded, but every time you play it, the CPU has to do work on it in order to give it to you. So by turning off the internet, that just means it's not going to have to download it anymore. But just because it's downloaded doesn't mean the CPU doesn't have to do work in order to play it for you. It absolutely has to do work in order to play that for you.
But I'm just feeling like because like it recognizes it, it doesn't have to do as much work. Is that the case?
Not really. If it's still trying to play that audio, it's going to be doing work on it, whether you're connected to the internet or not. So the main point is shut everything down that doesn't need to be open. Turn it all off. Don't make this CPU have to care about things that aren't important right now. Because the most important thing is keeping track of this uninterrupted stream of digital audio that's coming in. Because if it drops a sample in the middle of the recording, guess what? You got to do it again. You got to make the actor do it again, or the singer do it again. Like you can't. There's no way to get it back. Okay, so generally speaking, what's going to happen is it's going to allocate a buffer that should be large enough for it to collect this audio. All that digital audio is going to like fill up that buffer while the CPU is pulling stuff out of the buffer. And the idea is that it's hopefully pulling it out of the buffer just as fast as you're feeding it in. But if the CPU ever has to take a break and look at something else for a second, that stuff builds up inside that buffer until it comes back and gets more of it, right? And then you're never going to lose any of it. But if the buffer fills up before the CPU pulls anything else out, then what happens to the digital audio that's trying to get into the buffer? It can't fit. Buffer's full. So it just drops it. That data just disappears. Okay? So you want a big enough buffer to account for whatever problems the CPU is going to have keeping up. Okay? But the bigger the buffer, the more latency you have. Because all those samples have to go and sit there for a little while before it then goes through the computer. So the longer it has to sit there, the longer you have to wait to hear it. Or pass it on to whatever the next step is. And that's where you can get like audible echoes, for example, when you're like playing it back through your speakers, your headphones. And you're hearing it happen in real time in the mic, and then like noticeably, like a couple milliseconds later, it comes out of your headphones or your speakers. That's why. It's because you've got a really big input buffer that's, it's just literally waiting. It's holding on to the sound and not letting you hear it until a little bit later. And generally speaking, a lot of the digital audio programs now will try to figure out that buffer automatically for you. But there are plenty of times when you might need to manipulate it. You're always trying to find that balance between, latency and reliability. You want the big buffer to be big enough that you can reliably capture all the audio, but not so big that you've got too much latency. So that's something you can control in your software. Like Logic and Pro Tools, for example, you can control the size of that buffer. That is a definable parameter by you, definable by you. You can say how big you want that to be. Okay? So when the CPU is ready for it, it pulls it out of that buffer and does whatever work it wants to do. Yeah?
Is this a situation of like an it depends, or is there like kind of a good size for your buffer to be? I mean, I know like it seems like a lot of things kind of default to certain.
I mean, when you're recording, you want it as low as you can get it. When I'm recording, I try to get it down to like 64K, like 64 kilobytes as the size of the buffer, if I can swing it. And I can usually swing that if I shut everything down and don't let the computer do any other work besides just do this audio thing, then I can usually get it down to something like that and be okay, especially with how fast the processors are now. But when I first started doing this, 30 years ago, our buffers were a lot higher than that. They were like at least 1,024 kilobytes, if not higher. But now we can get them pretty low if you got a fast enough computer and you shut everything else down. Getting it down to 64. Some will even take it as far down as 32K, which is not very much, but that's pretty fast. So hopefully you got a fast computer. There's things you can do to accommodate that small of a buffer, like get a faster CPU. You can manage your data really effectively. We're going to talk about that in a minute. Like, where is the CPU having to put this information when it's done with it for long-term storage? And is that a location that is fast or slow? The faster your long-term storage media is, the lower buffer you can get away with, because the CPU can feed the data into that faster. Okay? So there's things you can do to make that work, but one of them is like reduce the number of input streams, because I'm animating this right now as one signal, but you could have many at a time. I mean, some out of your interfaces, you could have dozens of mics plugged in, and you would have dozens of input buffers that are going through this. And at that point, it might be really hard to keep the buffers that small, because the CPU has to tackle all of that. So you might have to increase your buffer sizes when you got a lot of tracks. Okay, but if it's just one, you can get it down pretty low. So what is the CPU doing? Well, it's doing whatever it needs to do right now. It's applying the EQ, the compression. It's putting the reverb on it. It's mixing it together with the other things. It's amplifying it. It's all those things you do. It's editing it. It's trimming stuff off. It's adding stuff. It's all the things that you do to the sound. The CPU has to do those things. Okay, and so when it's done doing that thing, it has to then put it somewhere. Okay? In some cases, it'll put it back out to RAM. In some cases, it will put it to a storage area. And so it just kind of depends on what you're doing. So let's kind of trace it through the typical things. So the way it knows what to do with it is based on what the software tells it. So you're going to be running a piece of software that we call a digital audio workstation, or DAW. If you say the word DAW, I'm going to roll my eyes, because I don't like it when we try to turn acronyms into words. I think that's silly. But that's just a me thing.
Like, what are your thoughts on scuba, Jason?
Yeah.
Yeah, I don't remember what it means. Submerged.
Self-contained underwater breathing apparatus.
Yeah, that one.
Lots of people say DAW, but I think, I think that's dumb. Because, it's not a word, it's an acronym. Don't turn an acronym into a word. And this is just because of my proclivity to really understand things. I really want to understand things. And the point is that an acronym means something. And if you turn the acronym into a word instead of an acronym, then it loses the meaning. You forget what it means. Yeah. It's just a little nitpicky thing for me. It's fine. I'm not going to fail you in the class or anything if you say DAW, but
Just a letter.
yeah, exactly.
Do you say MIDI or MIDI?
It's true, I do say MIDI. So even I am a walking conflict on this, but
Wow, yeah, I gotcha.
yeah.
You can say multitude.
Yeah. All right. So the digital audio workstation software, this is like Logic or Pro Tools or Sonar or FL Studio or Ableton or any of these things that you use. Okay, and it has instructions on how to do things to digital audio. Okay, and so you will, using some input devices, tell the software, I want to do this to this audio, and then the software will tell the CPU how to do that. They'll say, okay, here's how to do the thing that they want to do. They want you to add this EQ, they want you to compress it, they want you to mix it together with this thing, add some reverb, put it out here, and send it this direction. And so the software will send those instructions to the CPU. The CPU will happily comply and do its darndest to perform that operation. You got a question?
Yeah, so the software is never actually touching the audio. It's just saying,
No.
hey, they want to do this thing.
Yep.
Do the thing.
Yep.
That the CPU says, okay.
Yep. Yeah, the software just has the instructions about what to do with this never-ending stream of data that's coming in. The software is just saying, hey, this means that, this means that, this means that. do this with this part of it, do this with the other part of it, it's just telling the CPU what to do. And it knows what to tell the CPU to do based on what you tell the software. So you tell the software all the things you want to do. The software knows how to translate what you said into something the CPU understands. The CPU then performs that command and then moves on to the next thing it needs to do. Okay? So the software is telling the CPU how to do that. Okay? And so, there's a lot of personal preference involved with the software. I mean, you end up using the things that you like to use that make sense to you because that's your interface. And some interfaces make more sense than others. But these days, a lot of it's leveling out, and a lot of them kind of work the same way and do more or less the same thing. It's just kind of what you're used to. It doesn't really matter. The software itself, with a few exceptions. I mean, aside from like the actual processes, like plugins and things like that, some of those algorithms are better. Like there's a big difference between a mathematical reverb algorithm, like a calculated reverb algorithm, or a modeled, what we call a modeled one, versus a convolution reverb where it's doing a convolution process. That's a very big difference. It's still a digital audio operation, but the end result sounds a lot different. And so, that's where the software really matters, is more in kind of like the plugins and the processing that gets done. But, the part where it mixes everything together and everything, that's really boils down to interfacing for the most part. But the software does all that, okay? And so one of the things that the software is going to tell the CPU to do, for example, is, hey, translate this stream of audio into a picture that looks like this and show it to the user through a monitor, a video monitor, right? So the CPU is going to draw that wave, okay, that then it draws on the screen so you can see it. So that's one of the things the CPU is doing that has no impact on how good it sounds. It's just like it has to do that work. It has to convert that digital audio signal into a picture and put it on the monitor. And it has some hardware to do that. But some other things that the software might tell it to do is, hey, once you've done this thing to it, store it somewhere where you'll remember it forever. And it has a couple of options. There's going to be a built-in storage device, either a hard drive or more likely these days an SSD, a solid-state drive, that's going to be used as a long-term repository. Now, the problem is this one that's inside of your computer is being used for a lot of other things. So this drive is storing the operating system for the computer. So the actual operating software for the computer itself is stored here and constantly being accessed. The application software technically resides there. And also your data would reside there too. That's a lot of things to be coming in and out of that drive. And there's a limit to, just because the drive is 10 terabytes, for example, does not mean it can push all 10 terabytes in or out at one time. It can push much less than that out, in and out at one time. And so it's called bandwidth. The size of that digital pipe is only so big. There's only so many zeros and ones that you can push and pull off of that drive at one time. And a big chunk of that bandwidth is going to get chewed up by the operating system and the software and all that other stuff that has to be done. And it leaves a small chunk of it available to push and pull your digital audio. So one of the ways that you can get away with those smaller buffers, for example, and higher sampling rates and all these things is by dedicating a separate drive that only does your audio. And so that's what this is here. Some sort of external drive, or sometimes you can have a second internal drive, but the point is that this drive is only used for audio. You don't put software programs on here, you don't put other kinds of files on there, like you don't put your games on there. You don't put your operating system on it. You don't put nothing else goes on this thing. You don't put your like bootleg video library on this thing. You don't put anything on it except for your digital audio. That should be the only thing that this is used for. And if that's the only thing that drive is used for, then guess what? That big pipe of how much data can be pushed and pulled on that, the entirety of that bandwidth can be used for your audio, which means that the CPU can get your audio there faster. It can get it there faster, and it can get more of it there faster, which means more tracks that you can run at a time, smaller buffers, less latency, more processes you can do, just more of everything if you dedicate the drive to do the audio. And this is another one of those convenience versus quality trade-offs. It's a lot less convenient to plug an external drive into the computer and dedicate that to your audio. But the payoff is enormous. And I carry 2 drives with me. Okay? So I've got this one, and I have somewhere, oh, wrong pocket, and I have this one. Okay? So this one is a traditional hard drive. It's got spinning disks in it and magnetized particles and a little wand that moves around. But it's also like, I don't know, it's at least like a 4 terabyte drive, I think. Okay? It's not super fast, because hard drives are a lot slower than solid state drives, but it's got a lot of space on it. So I put audio on here that I don't need immediate access to. There's not a lot of bandwidth involved. Like I put my sound effects library on here. I put, archival stuff, like things that I just want to hang on to, that I want to be able to get to, but I don't want it to take up space on my computer. But I'm not necessarily going to work off of this drive. This is like, oh, I need those sound effects. I'm going to get it off of here. I'm going to load it into the system, and then, but I'm not going to be working actively. The computer's not going to be actively pushing and pulling data on this drive a lot. So this is the stuff that I put on it that I want to keep with me a lot, but I don't want it to take up space on my internal drive. But it's not like where I'm working. Okay? This drive is an SSD. It's a 500 gigabyte SSD that is super fast. This sucker will do 40 gigabits of data in and out per second, which is like 2 gigabytes a second.
How much was that?
I don't know, $150 or something. I mean, but it's not a lot of space. I mean, it's only 512 gigs. It's not a huge drive, but this is my dedicated audio drive. The thing I'm working on right now is on this drive. Like if I'm in tech for a show and I'm pulling up all those Logic sessions we're working on, they are sitting on this drive because this drive is super fast and it's got a really big pipe on it. And so I can push and pull a ton of data off of it in real time without no hitches. I can lower my buffers down really low, and everything runs faster, okay? And it's on here, the thing I'm actively working on. But because it's only the thing I'm actively working on, the projects I'm doing right now, it doesn't need to be big. It doesn't have to have my entire life's work on it. It just has to have this month's work on it, okay? And when the tech's over, I move it to this, or I have like some backup drives and archival drives and stuff that I put it on for really, really long-term storage. But this does not have to be this is why I didn't have to spend a lot of money on it. It was not super expensive. I mean, a high-speed SSD like this can be very expensive, especially with the Thunderbolt interface like this one has, which is what gets it up to that 40 megabits per second. USB-C tops out at 10 megabits per second. But Thunderbolt, you can get up to 40. So this is specifically a Thunderbolt one. So that, if you were trying to get 4 terabyte version of this, you're going to spend a couple $1,000s. But if you just need half a gigabyte, which is more than enough for your average project you're going to use, yeah, it's a couple $100. And well worth it, okay? because I never have to worry about running out of space on my startup drive. I never have to worry about in the middle of the recording saying, oh, sorry, drive's filled up. We just dropped the samples, or freezes up because it runs out or whatever, because it's always going to this drive, and this drive is really fast, and it only has the audio on it that I'm working on right now, and I leave plenty of space on it, and it's fine. So that is why, hopefully maybe now, after I've given you this pitch, you'll understand why this is part of our required equipment. When we talk about the equipment that we require you to buy to be a student here, it is the laptop, the Logic software, and that drive. It is that important that we consider it a core tool. More important even than having your own set of headphones, right? Having a dedicated, external, fast audio drive is so important, because if you get into the habit of using this drive, there's a lot that you're limited bandwidth. You have to increase your buffers, but also there's a lot of other stuff on there. And sometimes it's hard to find where your stuff is amid all that other crap that's on there. I mean, the number of times I've walked in here to a student, who is like eyes this big, sweat coming off their forehead, frantically going like, what is going on? I can't find my work. I spent days on it. It's due in an hour. And like, I can't find the latest version of it. The one that has my changes, I can't find it. And I go on there, and it's because they're digging through billions of files on their startup drive, because that's where they put it, and they can't find it. There's too much stuff there. They can't keep track of it. But if you're getting in the habit of putting that stuff on an external drive like this, and that's the only thing that's on this drive, you always know where it is. You never have to worry about what folder did I put that in. There's only one folder on this thing. It's the folder of the project I'm working on right now. And I save it to there. It's always on there. I never have to wonder, oh, is it over here? Is it over there? Where did I put it? It's always on here, okay? Super important. Okay, so you need this internal drive because the software has to run off that and all that kind of stuff. But don't have that be the thing that's storing the thing you're actively working on. And this external drive should be the fastest you can afford. Capacity on this is not as important as speed. If you can only afford one drive, then you're going to have to make a compromise between capacity and speed. Okay? But if you can afford to do two, like this 512 super fast SSD was a couple $100. Well, this 4 terabyte slow hard drive was like $125. So collectively, I spent like $300 something, but I got two separate things for two separate purposes. And anyway, so you'll have to figure out how to do that. But this cable, you want this to be the highest throughput connection you possibly can get, and these days that's Thunderbolt. Coming in a close second, well, kind of close, is true USB-C. A true USB-C connection can get you up to 10 gigabits per second. And behind that, the next fastest thing would be some sort of external serial ATA connection, which had a very short life. They thought that would be a bigger thing than it ended up being. And then behind that, you're looking at like a USB 3 connection, which will be at best 5 gigabits per second. USB 3, USB 3.1 can do up to 5 gigabits per second. And that's a pretty big difference. A lot of the drives that look like they're USB-C are actually just USB 3 with a USB-C connector on it. And so they look like USB-C, but they're actually running a USB 3 chip, which means you're maxed at 5 gigabits per second. So if you're buying a drive, look at that spec. Like, what is that maximum speed, read-write speed? If it says 5 gigabits per second, even though it's got a USB-C connector on it, that doesn't mean it's USB-C. Okay? But if it's true Thunderbolt 3 or Thunderbolt 4, and if it's an SSD, you ought to be able to get 40 gigabits per second in and out of that thing, which is insane. Very fast. if you have the other way around this, by the way, is to dedicate the computer to a single purpose. So like that's why like our QLab computers that we use for production, I say don't put any software on there that I don't approve. Don't store anything on there that I don't approve. Delete your show when it's done. There's nothing on those computers except the operating system and QLab. And therefore, there's not a lot of extra garbage on it. And so we just use that internal drive for the audio because we're only ever doing one show at a time. And there's nothing else going on. Those things don't even connect to the internet. They don't run any other software. And so that internal SSD is fast enough and has a high enough capacity and is less cluttered in a way that it works okay. You don't have to have an external drive to have it work effectively. But if it's a computer like your laptop you're carrying around with you that you have to do 300 other things for you, having that external drive is going to be really, really important. Questions so far? Okay. Well, as you can see, you've got digital data going onto this drive and coming back. So it's both directions. Same thing is happening on the internal hard drive. The blue is the audio, the digital audio. The green is all the other junk. Okay? So there's two different kinds of data if you're using the hard drive or the internal drive. But if you have the external drive, then maybe you only have the green stream going, which would be way better. The green stream is all the software and all the commands and all that kind of stuff. There is a thing called a driver, which is a piece of software that sits on the computer that tells the computer how to talk to your audio interface. All right, so it's a little piece of software so the computer knows when you plug that audio interface in, it knows what that is and how to talk to it. So there'll be a little driver doing a green digital signal, which is all the control information of like how to tell it to do stuff, issue the commands, and all that kind of stuff. Sometimes you'll forget to put that driver on there and wonder why the interface doesn't work. Why can't the computer see it? Well, you didn't teach the computer how to talk to it. And you teach it how to talk to it by installing the driver. Sometimes a lot of manufacturers these days are using what are called class-compliant drivers, where the operating systems have some built-in ability to understand how basic functions of an audio interface are. And as long as the interface doesn't go outside of those basic functions, then it automatically knows how to talk to it. It's called a class-compliant driver. And some interfaces will have a little switch on them. Because the class-compliant is basically limited track count or limited channel count, limited features and stuff. It's very bare bones. But then there's a switch where you can turn off the class-compliant, put it into like the super-duper mode where you get all the extra features. But then you need to install the extra driver because there's a lot of different things the computer needs to learn how to do in order to access all those features. So you just have to know which you need, but most of the time, if it's a nice enough interface, you're going to need a driver. Like this one needs a driver. You plug this in the computer, it's not going to do a darn thing until you install the driver and teach the computer how to talk to it. Okay, so at some point, the audio is going to be sent back out for you to listen to. Okay, so you can hear what the computer did, and that's going to come. You know, the computer's going to pull it off the drive, do the stuff to it in the CPU, and then it's going to send it back into RAM into something called an output buffer. For all the same reasons it needs an input buffer, it also needs an output buffer because it's now going to create this continuous stream of audio that you're going to listen to, and you don't ever want that to be interrupted. But the CPU is thinking about a lot of things at one time, and it's not always thinking about that audio stream, and so it needs to take a break every once in a while. And so it makes a buffer where all that audio builds up, and hopefully it just keeps feeding into the buffer as fast as it's getting pulled out of the buffer. But if the buffer ever fills up, like if it's more likely that the buffer will empty out, right, than fill up. More likely the audio is going to leave the buffer and the CPU is going to get distracted and forgets to replenish that buffer, and you'll have a dropout in your audio. That's the more likely happen. But it is, I guess, possible that it could fill up. But more likely it'll be empty. So what you're looking for here is you want a big enough buffer that the CPU can take long breaks without you running out of audio. So your output buffers tend to be much higher than your input buffers. Output buffers can be, like the default output buffer in QLab, I think, is 1024 kilobits or kilobytes. Not sure which. That's usually the default, but it'll let you change it in the QLab settings. You can take it down as low as you want or as big as you want. But if you're having dropouts in QLab, if like you're hitting go and it tries and then like something weird happens and it can't play at all, you might need to increase your playback buffer. And that's a controllable parameter in the QLab settings. You can make a bigger buffer. And the only difference is like what that means is there'll just be more time between when you hit go and when you hear the sound. But even if you go to 2,000 something kilobits per second buffer, depending on your sampling rate, I mean, that could only be 2 milliseconds of latency, which in most cases, I mean, you're not going to notice that 2 milliseconds between when you hit go and when you hear it. But if you need it really fast and you don't need that latency, sometimes you might want to separate things out. For example, I've done shows before where I've had 2 operators. Or I've had one doing the QLab, which is playing back all the really big stuff that has the big playback buffer and has that couple of milliseconds of latency. And then the stuff that needs to be really fast, like the sound effects that are timed really tightly with action and stuff like that, that'll be on like a digital sampler with a keyboard that is instantly accessed. And you hit the button and you immediately get it. And you'll have an operator doing each. I'll have 2 operators. One doing the instant stuff on a sampler with no latency, and a different operator hitting go on QLab that has latency and is handling a lot more data. So it just depends on what you're doing, but you can manipulate that output buffer. And it's usually going to be a lot bigger than your input buffer. So that data then goes back into the audio interface through the interface controller, which then realizes what it is and sends it to this, the digital to analog converter. This is just a backwards version of the ADC. It takes that digital data, those digital numbers that are encoded in the samples, and converts it to a voltage value in real time. And coming off of that is now the analog voltage signal again. Now changed in however way you had it messed with inside the computer. It's now an analog voltage, and at that point it connects either to your headphones, or you can connect it to some monitor loudspeakers, or whatever you want. A mixing console. In the case of QLab, that's what you would do. You'd connect this interface to a mixing console. But in some cases, like these days, you don't have to convert it to analog yet. You would actually, your audio interface would be like a Dante interface or something that keeps it in digital. It just tweaks the codec a little bit and feeds it still in digital mode into your mixing console, and the mixing console is what converts it to analog later. That's fine too. Just depends on what you're doing, where that digital analog converter is, but it'll be somewhere. Eventually, it has to become analog because loudspeakers are analog. So it's got usually at the very least, it will turn into analog inside the amplifier, the power amp. It'll that's usually the point of no return, where it has to be converted to digital at that point in order to push that loudspeaker. Okay, that's the basic process. That's what's happening when you're doing sound on a computer. That's what the computer is doing and how it does it. And understanding this, if you truly understand this, you will have a better experience when you're doing it. I mean, like Lee, you've brought up a couple of examples already of like problems you've had with this, right? It's because you didn't understand it. You didn't know what was going on. And if you don't understand what's going on, how could you ever possibly fix it?
Honestly, what fixed it for me was just the storage part. Like external hard drive fixed
Yeah.
every problem because I couldn't find it.
Yeah. So sometimes if you've got a buffer problem, your buffer is either filling up or emptying out too fast, and you can't figure out how to manipulate the buffer, one of the ways you can help that problem is like moving to a faster external drive or changing your sampling rate or something so that that buffer is better right-sized for the speed of the computer. There's lots of other ways to attack that doesn't necessarily involve manipulating the buffer, but you can usually manipulate the buffer if you know where to look for it. Yeah, Eric?
So like, if you open up a session to your external hard drive, but like you said it was going to be faster, but does it still need like risk of overheating a computer?
No, because the heat happens here.
Oh, right.
Well, yeah, but I had some problems with running Pro Tools through my hard drive, and I still hear the heat coming through.
Well, the heat is in that case is generated by the CPU, right? The CPU is just doing a lot of work, and you might have a less efficient CPU, and so the CPU is just generating a bit more heat than you would like, and that's a natural byproduct of a CPU. Remember when we took that computer apart last week, trying to get that big heat sink off of it that was this tall, that was designed to soak up all that heat. That was the hardest part. And so, yeah, when you start making that CPU do a lot of work, its natural byproduct of that is a lot of heat. And that doesn't really have anything to do with the drive. But these drives can get hot too. So let me show you a couple of examples of some of these concepts and how they might appear. Yes, please. So here's my external drive. So here's a few projects I'm kind of working on right now. Let's see if I can pull something up that you could recognize. This. Something else. Oh, I'll do this.
Jason,
Yes.
while this is open, so if you were to have like large sample libraries or large like virtual instruments,
Mm-hmm.
you wouldn't want to keep all of those samples on your working drive, right? You would say, okay, for this project, I think I need this
Yeah.
piano and that other and this
Yeah.
other, and then pull those over.
Yeah, because once you load that into the session here, hopefully you have your project settings set to copy any of that external data into the actual project set, and so it'll be put onto your active drive as part of that
Okay,
process.
So just by basically opening an instant of whatever virtual instrument,
Yeah.
it pulls all of those samples into the thing.
Yep.
Okay, so you would just leave everything on yonder hard drive, and it would copy.
Yep.
Okay.
So yeah, for example, if I save a copy of this project, I have this option of, do you want to copy the audio files and the sampler audio files into the project? And if you have that checked, then anything that is on an external library, it's going to make a copy of it and put it in the folder for this project on your active drive. And that way you're not that way you don't need the external drive anymore, your big storage drive, right? That's how I do it. So that's why I have like my sound effects and samples and stuff on here. But once I pull them in, then they're part of the project and I don't need that anymore. Right. So let me show you a couple of things. So if you go into your audio preferences here, this is where you set your I/O buffer size. And in Logic, it's one setting for both. You can't manipulate them separately. And your options are 32 samples or all the way up to 1,024 samples. And it'll tell you, based on how high your buffer is, how much latency that's going to be. So right now, it's 7.2 milliseconds round trip. If I take it up to 1,024, it's 50.7 milliseconds round trip latency. That means audio comes in on the microphone, goes through everything, comes back out to the headphones, 50 milliseconds difference in time. And 50 milliseconds is, right? That's about 50 milliseconds. That's noticeable. Okay? Hopefully you can recognize that from SoundGym now. 100 milliseconds, 120 milliseconds is, okay? 50 milliseconds is really fast, okay? But noticeable. But you take it down to 64, that's 7 milliseconds, you're not going to hear that. Right? You're probably not going to notice that as an audible echo. Okay? So that's where you're going to manipulate that there. Let me show you where it is in QLab. So I think think I've got a QLab file. Yes, here we go. So here's a QLab file for a show I'm working on right now. And you know you have the workspace settings, right? And this is like specific to your show, you know, preferences and stuff. But QLab itself has some preferences over here. And this is where you can manipulate things like your hardware buffers. So these are all the audio interfaces I have on my computer right now. I've got a lot. Some of them are like virtual ones. Some of them are real ones. But depending on which one I want to use, like if I want to use the Scarlet, which is this big red one, it's currently at a 512. It looks like they're defaulting to 512 now instead of 1024. And I've been saying this wrong. It's actually samples, I realize now, not kilobytes. It's the number of samples you can store. Okay, so you can take it all the way up to 1024 if you want, or you can go lower. But the lower you go, the faster your computer needs to be in order to deliver that. But it'll get you the information quicker. But that's where you manipulate that. And I've seen students have trouble sometimes with like QLab just not keeping up, and that's where we'll go. It's like, well, what's your buffer? Let's go set it. Maybe we need to increase that, and that's fine. Okay, so that's where you set that. Questions? No? Okay. Well, let's take, because it's 2:20, so we still have about 45 minutes. So let's take a quick 5-minute break and let's go out and hook up to the booth out here and try to do this. Okay? I think that'll be good because that's what you're going to have to do for the project.